In this video, we're going to talk about the stereochemistry of the SN1 and SN2 reactions. In the previous video, we were talking about the differences in the mechanisms between the SN1 and SN2 reactions. Now we're going to talk about why we even care about the mechanism. And the reason is that the product, or the stereochemical outcome of the reaction, is dependent on the mechanism. For example, as you can see here, in the SN2 reaction, only one stereoisomer, or one product, is formed. However, in a reaction that proceeds through an SN1 mechanism, you see a mixture of products. This has to do with the fact that we proceed through a carbocation intermediate, and the carbocation intermediate loses stereochemistry, so the nucleophile can then attack from either side. Let's take a look at this in some detail. As you can see in the first step, the leaving group falls off, and that gives us a carbocation intermediate. The carbocation is sp2 hybridized, and when it becomes sp2 hybridized, that changes the stereochemistry. So now the methyl group, the phenyl group, and the ethyl group are all in the same plane. That means that the nucleophile, the I- shown here, can attack from the front, and when it does, you would get this product on the bottom right here, or it can attack from the back. And in that case, you would get this product here on the top right, where the nucleophile comes in from the back. So because in that coordination step, where the nucleophile forms a bond to the carbocation can occur from either side, we end up with two possible products. Now the relationship between these two products, of course, are enantiomers. And we see the enantiomers in approximately equal amounts because the approach of the nucleophile is approximately the same from either side. This is another picture trying to show you the attack of the nucleophile from either side. In this case, it's coming in from the right to give this product. In this case, it's coming from the left to give this product. So hopefully you can see the differences in the two approaches and how we end up with the two different products. In this particular example, we're getting a racemic mixture, a mixture of enantiomers, one being R and one being S. It's important to note, however, that if we have another stereocenter elsewhere in the molecule, we would get a mixture of diastereomers rather than a mixture of enantiomers. In this example here, you can see in the first step, the heterolysis step, the leaving group falling off, to give the carbocation. This carbocation is chiral because there's another stereocenter in the molecule. Now in the coordination step, if the nucleophile comes in from the front, we get this product shown here. And if it comes in from the back, we get this product shown here. The relationship between these two products are diastereomers, not enantiomers. Also in this case, because you have that OH that is sticking out towards the back a little bit, it might affect the approach of the nucleophile, so we're not necessarily getting a 50-50 mixture here. In the SN2 reaction, we formed only one product. So we can say that this reaction is stereospecific because we see only one stereoisomer formed. What happens in the SN2 reaction is shown here. Remember that the nucleophile attacks at the same time that the leaving group falls off. The transition state is shown here. That's what that little double dagger means. It means a transition state. Those dotted lines represent half a bond. So the leaving group is falling off at the same time the nucleophile is coming in. That means that we're only getting one product here because the nucleophile had to come in from the back. This is referred to as backside attack. If you can see what the nucleophile is doing, it's essentially pushing these three groups here out a little bit. And so when you're thinking about this, you want to visualize an umbrella. The nucleophile comes in and it pushes the other three groups out. So as it kicks the nucleophile out, it also pushes the other groups to the other side just a little bit. Now, why does the nucleophile have to attack from the back? Why can't it come in from the front? And one way to think about this concept is to recognize that there is a charge repulsion that's coming from that leaving group. In this example here, this would be a leaving group shown here. And here's our nucleophile. The leaving group is pretty electronegative, so the negative charge on the nucleophile is going to have a repulsion when it tries to get anywhere near that leaving group. On the back side, however, Notice that we have a delta plus, or a positive charge buildup, so the nucleophile can now come in from that back end. This is the concept of going from electron-rich to electron-poor. So think of the carbon as having a big delta plus, and our nucleophile, of course, has a negative charge. This means that anytime we have an SN2 reaction, the attack of the nucleophile comes from the back, so it looks like the stereochemistry is changing or flipping. Whereas in the SN1 reaction, we're getting a mixture of attack from the front and the back because the carbocation has no stereochemistry. In the next video, we're going to compare and contrast the E1 and E2 reactions and look at the mechanisms for those reactions.